Welcome back, calculus fans. Today we're into section 6.3, which is going to shed a little bit more light on the definite integral. I've included a table from the textbook that gives some of the more important rules about definite integrals. And these will actually make a lot more sense after we learn a little bit more about the definite integral in the next section. But for right now, we simply state them there, and you'll be able to read along and follow them, hopefully, soon. Okay, so what we're going to do now is going to be a little bit messy, but it's going to be shed a lot of light on this concept of the integral, the definite integral, as an area. So let's begin with this. We know that if we have let's say a set of n numbers. So we have a1, a2, all the way up to a sub n. The average of these finite numbers is simply the sum of all of them, as k goes from 1 to n, of a sub k, divided by the total number of them. So that's a feature that you have known pretty much all your life. The big question that we want to put out here is, how about the average of the y values for a continuous function over a closed interval? So this requires a little bit of thinking, and it takes a while to really get the feel for it. It's really simple for us to think about adding up n numbers and dividing by n. But when we talk about the average of all of the y values on a continuous function on a closed interval, well, what we're talking about is adding up an infinite number of y's and dividing by infinity. And that really doesn't make a lot of sense. So what we'll look at now is the algebra behind this, and I think you'll come up with a rather surprising result. Okay, so here we go. This is what's known as the average value of a function over a closed interval. Now, here's what we're talking about doing. We're talking about adding up a lot of these f of c sub k's as k goes from 1 to n of 1 over n. Now that's just n of them, but now what we're going to do is take the limit as n goes to infinity. And these are c sub k's that are in the interval a to b. So once again we see, as it's popped up so many times, this concept of a limit. So really what we're doing here is adding an infinite number of these values of the function, and we're dividing by 1 over n as n goes to infinity. So it's similar to adding up a bunch of values and dividing by the number of them, except here we're letting that number go to infinity. So here's the mathematics behind it. This is equal to the limit as n approaches infinity. What's what we do here? Of 1 over b minus a, where the heck did that come from, times the sum as k goes from 1 to n of f of c sub k. Okay, now I'm going to get rid of that 1 over b minus a by multiplying by b minus a. And remember, we had this 1 over n here. Well, I'm simply going to write it there. Okay, so let's see if we can get this to fit. Limit as n goes to infinity of 1 over b minus a, which really doesn't depend upon n times this sum as k goes from 1 to n of f of c sub k. And now, what's this? Well, if I take the length of the interval, which is b minus a, and divide by n, you should remember that that's simply an expression for delta x. And now, if you can just imagine taking this b minus a, 1 over b minus a, and bringing it out in front, because it doesn't depend upon n, then what I'm left with is this expression as n goes to infinity, and you'll remember that that is simply what we call the definite integral, which means the area under this curve from a to b. And that, my friends, is a big deal. And so this right here is what we call the average value of the function over the interval a to b. It's sort of like adding up all the y values and dividing by n. But when we play around with it, what we see is it's simply the area under the curve divided by the length of the base. So we'll examine that idea in a second, geometrically. So once again, believing that a picture is worth a lot of words, we see again that the definition of the average value of a function on this closed interval a to b is simply the area under the curve divided by the length of the interval. Okay, so let's look down at this picture. In the shaded region, that's equal to the area under the curve from a to b, written like that. Well, think about a rectangle, and think about a rectangle that's really nice, and think about a rectangle whose height is exactly equal to the average value. In other words, what I'm suggesting here is that the height that I've chosen here is exactly equal to that value. So, if I take that height and multiply it by the base, which is b minus a, I'm essentially doing this. I'm taking the integral from a to b of f of x dx over b minus a, that's this height, and then if I multiply it by the base of this curve, which is b minus a, what I get is the area under the curve. So the idea here is that this average value is a special height. It's a y value, and it's the height of the rectangle which has the same area as the area under the curve. So it looks like I probably drew that height a little bit too high. But essentially what we're seeing here is that the area of the rectangle is exactly equal to the area under the curve. And that's the significance of the average value of a function on a closed interval. So hopefully the picture in this little bit of algebra will make sense to you. Alrighty, so now let's consider a theorem that's called the mean value theorem for definite integrals. And it says this: f is continuous on AB, then there must exist a c such that f of c is equal to the average value, which is basically what we were saying before, but here this will be a bit of a proof for that. Now, here's what we know. We know that since f is continuous on the closed interval AB, then by the extreme value theorem, there is a min, which we'll call m, and a max, which we'll call capital M. And those two numbers are promised by the extreme value theorem. So therefore, what we can do is say that the area under this curve from A to B has to be greater than or equal to the little rectangle with M as the height. There we go. And less than or equal to the rectangle that has capital M as its height. Well, what that means then, if we divide by B minus A, is that M is less than or equal to, well, what am I going to be writing here? What is it? That's the average value of f on the interval A to B. And we've said that's a y value. So this, the average value, is a number. And it's between the minimum and the maximum. So what we can imply, therefore, by the intermediate value theorem is that there is a C in the interval A to B such that f of C is equal to, I'll just write it as the average value. And that's a big deal. And f of C, as we said before, this is that magic height. It's the height of the rectangle with base B minus A that gives us the exact area under the curve. So think about that a little bit, but that's a big deal, this theorem, and it'll come to play a rather significant role in the next section. So here's a simple example. Find the average value of x squared over the interval 1 to 3. And so we know that it's going to be 1 over 3 minus 1 times the definite integral from 1 to 3 of x squared dx, which is equal to, and here's where we use our calculator to evaluate this. And on the TI-89 or on the Inspire CAS, doing that is a pretty simple operation. And so this is equal to, by using our calculator, 1 over 2 times 26 over 3, or 13 over 3. Now, what does that mean? Let's take a look at the picture. So down here we see the graph of y equals x squared, and we're looking at it from 1 to 3, and the shaded region is the area under the curve. The significance of the average value is simply that if I were to draw a height whose value is 13 over 3, then as we've said before, the area of that rectangle, which is 13 over 3 times 2, is exactly equal to the area under the curve, which we've seen by our calculator is 26 over 3. And there's a simple example. One of the things that we will learn beginning in the next section is how to compute this definite integral by hand and not rely on our calculator. And luckily, you'll see that evaluating this by hand is a lot simpler than the way we evaluated it in the previous section. So, hold your breath. Next section is a big one. It will tie together the big ideas of differential calculus with what we are learning now, which is integral calculus. See you then.